Hi, this is Professor Merrill Lichty. In this video, we're going to talk about hypothesis testing done with p-values. Previously, we have established the framework for hypothesis testing, and we did that by in a couple different ways. The first was comparing a test statistic to a critical value and determining if the test statistic lies in a rejection region. If it does, then we reject the null hypothesis. We also looked at confidence intervals and the relationship that there is between those and the critical value approach. And turns out that there is one more way to do it, and that is to use what's called a p-value. And that's what this video is all about. So let's look again at our credit card processing time example from the previous video. You will recall that we were testing the null hypothesis that the average processing time for credit card charges was 40 seconds, and some new process came along, and the claim is that the new process is less than 40 seconds. So we had a sample size of 50, a standard deviation of 4, and an alpha level of 5%. Notice that sigma is known here, so we used the z test statistic. The null hypothesis is mu is equal to 40. The alternative is that mu is less than 40, so that's a one-tailed or one-sided hypothesis, and since alpha is 5%, we want a rejection region that is the lower 5% tail in the z distribution. We figured out that that is corresponding to a value of negative 1.645, which is the critical value in the z world. And so if z is less than that, that tells us to reject the null hypothesis. And again, this is just the critical value approach to hypothesis testing. So what if we didn't know what the critical value was? We still know what alpha is, though, 5%. And we know that we're going to reject if we're in the rejection region. But what if we're told that the area to the left of the test statistic is equal to 6%? So even if we don't know the value of the test statistic, can we make a conclusion for this test? Well, the answer is yes, because the area to the left of our test statistic is 6%, which is bigger than 5%, which is our alpha level, which makes our z value, our test statistic, fall clearly not in the rejection region. Okay, let's look at a different scenario. We still don't know what the critical value is, and we also still don't know what the test statistic is, but we're told that the area to the left of the test statistic is equal to 3.2% or 0.032. What's the conclusion of this test? Well, if the area to the left of our test statistic is 3.2%, that's less than 5%. That means our test statistic has to be in the rejection region. And so we would reject the null hypothesis in favor of the alternative hypothesis. So it turns out it doesn't matter if we know what the test statistic is, as long as we know what the area to the left of the test statistic is and the area corresponding to the rejection region. So here is then the definition of the p-value. It's just the area to the left of the test statistic, and at least in the left-tailed test as we have here. And the test can be concluded based on comparing the p-value to the alpha level. If the p-value is bigger than or equal to alpha, that means do not reject H0. If p-value is less than alpha, that means we're going to reject H0. So in summary, if p is low, H0 must go, and that's kind of a catchy little phrase you should memorize, because it's always going to be true when we're dealing with hypothesis testing. If p is low, H0 must go. In the previous example, we did a left tail test, but we need to figure out what a p-value means in terms of a right-tailed test. So if h1 is a greater than, then the p-value is not the area to the left, but it's the area to the right of the test statistic in the z or the t distribution. If h1 is a less than test, then the p-value is the area to the left, as in the example that we just did. And if the alternative hypothesis is not equal to, or a two-tailed test, then the p-value is twice the test statistic's tail area, where the tail area is the smaller of the areas to the left and to the right. The smaller the p-value, the more extreme the test statistic. But it doesn't matter which type of alternative hypothesis we have, or which, if we have a one-tail, right-tail, left-tail, or two-tailed test, the little phrase, if p is low, h0 must go, is still going to be appropriate and what you want to use. We can interpret the p-value as being the observed significance level of the test. That's one way to think of it. Another way to think of it is the probability of seeing something more extreme than what was seen the first time, or with the test statistic that we observed. What's the probability of seeing something more extreme than that if, say, we were to repeat this test? The smaller the p-value, the more significant the test statistic is. And so for p-values that are less than 0.01, less than 1%, those are considered highly significant. So if you had an alpha level of 1% and you rejected the null hypothesis, that means your p-value is less than 1%. And p-values are very useful because you don't have to specify alpha. You can just say, what's the p-value? And whoever you're reporting the p-value to can determine their own value of alpha, their own level of alpha. P-values between 5% and 1% are considered to be significant results, so not quite as good as a highly significant result, but still very good. Alpha, of course, is the 5%, is an alpha of 5% is the default that many people use, and that's what you should use if it's not specified. If you're going to determine if you're going to reject the null hypothesis, and all they give you is a p-value, then use alpha as 5%. Make that comparison. Values between 10 and 5% are considered weakly significant, and anything bigger than 10% is generally considered to be insignificant, meaning there's no real evidence to reject the null hypothesis. So let's look at this again. The p-value is just a probability that, given the null hypothesis, if we were to obtain a test statistic in a new sample, in other words, repeat the experiment, that the new sample would be more extreme than the observed sample, the one that we saw the first time. And so what this is essentially telling us is that if the p-value is small, for example, the result we obtained is not very likely to occur when h0 is true. And if that's the case, then that suggests that h0 should be rejected. One way to think of this is if you were to try and explain the difference between the hypothesized value of mu and the observed x bar, you could say, is that difference big? And if the difference is big, then that would suggest that the alternative hypothesis is true. So what does it mean to have a big difference? Well, that depends on the alpha level, but you can measure the p-value by saying, assume the null hypothesis is true and find the probability of being further out or more extreme than what was observed. That's the probabilistic intuition. The operational interpretation, again, is if p-value is low, h0 must go. And what we mean by that is if the p-value is less than alpha. So where this becomes useful is someone can come to me and say, here's my null hypothesis, here's my alternative hypothesis, and here's the p-value. And I don't have to know what the test statistic is, the critical value, anything else that might be relevant if I'm doing some other type of approach, all I have to know is what the p-value is. And then I can use my own alpha if I want as well. Okay, let's go back to our example that we did in the last video where we have the visa, and you'll recall from that video and that output that the test statistic we saw was negative 2.74. And so to find the p-value, all we have to do is find the area under the curve to the left of that, because this is a left-tailed test. So the probability of being more extreme than what we observed is going to be the p-value. And if we look this up either using the table or the software, we see that the p-value is very small, 0.0031, which means the area under the curve to the left of that, or the probability of being more extreme than what we saw, is very small, which does not lend credibility to the notion that the null hypothesis is true. It says if the null hypothesis is true, it's very unlikely to see the value that we did, and that's evidence in favor of the alternative hypothesis. So back to our little phrase, if the p-value is low, H0 must go. So is the p-value low for alpha equals 5%? Yes, it's low. 0.0031 is less than 0.05, so that means that we should reject the null hypothesis, which is consistent with what we did with the critical value approach and also the confidence interval approach. So let's look at the other example with the Quacker granola. Again, we have the null hypothesis that mu is equal to 24 versus the two-tailed alternative that mu is not equal to 24 and alpha is 1%. Sample size of 22, degrees of freedom 21, and you'll remember our test statistic was 2.233. And since this is a two-tailed test, the p-value is going to be twice the test statistic's tail area. And so we can't really look that up in the chart in the book, so we're going to have to turn to the software, and we can use the t-distribution in Minitab to do that, or you can also do it with Excel with the function t.dist, and I'll let you look that up on your own. But here's what we get. 2.233 has 98.17% of the area to the left of it, which means there's 0.0183 to the right. And we said if we have a two-tailed test, it's going to be, the p-value is going to be twice the area to for the smaller tail, smaller of those two tails. So it's going to be 2 times 0.0183, which is 0.0366. Incidentally, if you look back at the output, you will find that number given to us for free by Minitab. And so let's look at the output in Minitab. If you go stat, basic statistics, one sample t, put in the data that you can find in the PowerPoint that goes along with the last video, we see that we have the test of mu equals 24 versus not 24. And we get all of this output here, 99% confidence interval, the test statistic t, and you see the p-value is given to us here, 0.036. And at the 5% level, we would reject that null hypothesis, but at the 1% level, we do not reject. And that's kind of the point in giving p-values, is to allow people to see what's the smallest level of alpha for which we would still reject the null hypothesis, and that's going to be the p-value. So in this case, if you think alpha should be 1% and I think it should be 5%, we've got a difference of opinion. That's a subjective thing. We can try and reconcile that somehow, but one would say there's got to be highly significant evidence, and the other would say there's got to be significant evidence, and you have to decide whether you're going to reject or not.